random variable given y is equal to expectation of x squared. So we just saw that expectation of x, so if you have x given y and you compute its expectation, this is equal to the expectation of x actually. So this will be true if you have squares actually. Okay? So the expected value of the conditional variance, okay, is this quantity. Drive it explicitly if you don't understand it. And the third thing that I would like to talk about is really the variance of expectation of x given y actually. So the variance of expectation of x given y. Okay, so this is expected value of the variance actually. You can ask a question. Okay, if expectation of xy is a random variable, then can I think about computing the variance of this random variable? Because I already know the expectation. So expectation of x given y is a random variable. Okay. The question is, what is its expectation? We know the answer, that this is equal to expectation of x. You can ask another question, okay, what is the variance of the conditional expectation? Okay. What is the variance of the conditional expectation? The answer is that the variance of the conditional expectation is this interesting formula. Okay. Is this interesting formula. The variance of the conditional expectation x given y is equal to expectation of x given y squared minus, okay, expectation of x given y squared minus expectation of x squared. Okay. Expectation of x squared. This is going to be the variance of x actually. Okay. So this is a formula that you got to verify for yourself actually. Okay. And here is the proposition. I'm also leaving this proposition as an exercise for you. Okay. And this proposition is that I know that how expectation of x is related with the expectation of conditional expectation. So expectation of x is the expectation of conditional expectation. The question is, can I relate the variance with the conditional expectation? The answer is yes actually. The variance of x is equal to the expected value of the variance of x given y plus the variance of expectation of x given y actually. Okay? X given y. This is what is really the variance of it actually. Okay, so the variance of x is the expectation of variance of x given y, which we know this is the quantity, okay, and the variance of expectation of this x given y is also this quantity. Okay, I made a mistake. The variance of expectation of x given y is not expectation of x squared, but expectation of x whole square actually. Okay, so now by adding these two, okay, you can immediately deduce this identity. So if you take the variance of expectation of x given y, and if you, for example, take the expectation of x given y and add them. So when you're going to add them, this and this term will cancel out, and what will remain is expectation of x square minus expectation of x whole square, okay, and which is equal to the variance of x. So you get this interesting formula of computing the variance of x through the conditional expectations actually, and conditional variance. So in other words, Variance of x is the expected value of the variance, conditional variance, and plus the variance of the conditional expectation. Okay, so we already proved it. So the only thing that we need to verify is first. So you try to write a proof for first 2 and 3. It's not difficult actually. Okay, just apply the definition and try to write a proof for it. So that will be the proposition. So what does this proposition is telling you? The variance of x given y can be written as this formula, and you can write this variance of xy in alternative formula, so we know that how to do it. Once you have it, then since this quantity is difference of these two quantities, and these both quantities are random variables, so variance of xy is also random variable. Now, if you compute the expectation of this variance, the task is to prove that this would be equal to this expectation actually, and it's not difficult. So take the definition of expectation and apply expectation onto both sides. So when you're going to do it, so you're going to get expectation of x given by whole square, and expectation of x square given y, which will be expectation of x square by previous proposition. So 2 is almost already proved. The only interesting thing would be to prove 3, that okay, if you compute the variance of expectation of y, you should get this number. Okay, you should get this number. And once you get this number, you add these two, you get this interesting proposition that you can compute the variance of a given random variable through what do you call expectation of the variance and the variance of the conditional expectation. Expectation of the conditional variance and variance of the conditional expectation. Okay, so this is what is really one of the example. Let's do one example based on it actually. Okay, let's do one example based on it. Let's do an example based on it. Okay, so let's do one example based on the formulas for, say, computing the expectation through the conditional expectation and computing the variance through the conditional expectation actually. Okay, so imagine there is a train depot. Okay, so you may, so it's a train depot, you can call it a train station actually. Okay, let's call it train station or maybe train depot. Okay, and assume that n of t represents the number of people that arrive at this train depot by time t. Okay, time t. So the n of t represents the number of people that arrive at depot by time t or up to time t. Okay, and assume that on this train depot, so this is the time when people arrive, and t is the time when the people arrive. That could be any time. Okay, obviously if they want to catch their trains, they have to be on time before the time. Okay, so n of t represents the number of people that arrive by on the train depot by the time t, and say y represents the time when the initial train arrives, or the train arrives on the station or depot actually. So y is representing the time when the initial train arrives or the train arrives actually. Okay, Now there are two given piece of information that n of t has a Poisson distribution. This is my assumption. Poisson distribution with parameter lambda t, while the train arrives at any time. For example, the arrival time of the train at depot is y, and this has a uniform distribution over the interval 0 to t. Okay, over the interval 0 to t. So what we have to compute, so the question that we will like to deal is basically this. Okay, is basically this. What is the expected number of the people that arrive on the train depot by the time y, in other words, by the time train arrives, and what is the variance of the number of people that arrives at the station or the train depot by the time y, in other words, by the time that the train arrives actually. Okay, so this is what that we are interested in. So we want to compute it. Obviously, we want to compute this piece of information through through conditional expectations and conditional variances actually. Okay, so we want to compute these piece of information through conditional expectation and the variances, the formulas that we developed for them actually. Okay. By the way, there is another thing given. There is another thing given that y and n are independent. Okay? Y and n are independent. The number of people that arrive on depot is independent of the time that, say, the initial train arrives on the depot actually. Okay, so this is another assumption actually. So let's compute, for example, conditional expectation. Let's start with computing the conditional expectation. So let's compute the conditional expectation of number of people that arrive up to the time, for example, up to the time when train arrives, in other words, the time y, given that the train arrives at a time small t. So if the train arrives at a time small t, what is the expected number of the people that arrive by a time t actually? So I can say that this is same as expectation of n of t given y equal to t actually. So I can write it in this manner. Now, what we know about n of t and y, that they are independent of each other. So knowing this information is not going to add any information into the expectation. So this would be same as the expected value of n of t. Now, what is the expected, what do we know about n of t? That n of t has a Poisson distribution. So if we know that n of t has a Poisson distribution, then we also know its, expected value and its variance actually. So the expected value of n of t is really equal to lambda t. So this is lambda t. Okay. So the Poisson distribution with parameter lambda has expectation lambda actually. So therefore this must be lambda t. So I can say that the expected number of people that arrive by the time y, and this is the time at which train arrives, given y, given y, where y is any time. So if this is t, then you have a t is equal to lambda y actually. So if I substitute, for example, y equal to y, so you're going to have lambda y. So the expected number of people that arrive on the train depot by the time y, given that the train has arrived at the time y, is equal to lambda y actually. and I want to compute the expectation of this. So what should I do? Compute the expectation from both sides. Then I know that this conditional expectation is really the expectation of n of y, okay, and this is equal to the expected value of what we call y actually. And what do we know about y? That it's uniformly distributed over the interval 0 to t. So what should be the expected value of y? So the expected value of y is going to be t upon 2 actually. Okay. So use the formula for expectation of the uniform distribution actually. So we know that it's going to be t upon 2. So it's a plus b upon 2. So it's going to be, so if the uniformly distributed over AB, so a plus b upon 2 is the average, so you're going to have 0 plus t upon 2. So this is the expected number of the people that arrive by time y on the train depot, where y is the time of the arrival of the train. So this is the number of people that will arrive. It depends on the time, okay, interval, where in what interval train arrives, and what do you call, depends on the lambda actually, the number of people, the frequency of the people that arrive on the, what do you call, at the train, at the station actually. Okay, so this is what we have. The next thing is to, what do you call, we want to compute the variance of n of t. So for variance of n of y, I'm going to use my formula which we developed previously, that the variance of a random variable is the expectation of the variance plus the variance of the conditional expectation. Expectation of the conditional variance and variance of the conditional expectation. So expectation of variance of n of y given y, okay, plus variance of expectation of n of y given y. Okay, this is what is the piece of information that we know that we need to compute. By the way, we already know what is the so for example, let's start with computing this. Okay, let's start with computing this. So I know that the expected value of number of people that arrive by the time y, given that y is the time of the arrival of the train, is equal to lambda y. Is equal to lambda y. And I know the distribution of y. So if I want to compute the variance of this would be same as computing the variance of lambda times 1. But this should be same as lambda square times variance of y. Okay? This would be equal to the lambda square times of variance of the y. And what is the variance of the y? So y has a uniform distribution over the interval 0 to t. So you can actually see that the variance of this y is going to be lambda square t square by 12 actually. Okay, so this is going to be the variance of it, which is b square minus a square over 12. Okay, so we know the formula, so we can deduce this. So I know that this variance is lambda square t square by 12. So the next thing would be to compute the expectation of it. But for computing the expectation of it, first we need to compute the variance of n of y given y. And once we know this, then we can compute the